All right, how's everybody's fall break? Good? Too short, yeah. Okay, anything exciting to report or, All right, good. So, get started with our upcoming 2 weeks. So we are here on Monday. Today we will finish talking about AVL trees, and Wednesday we will talk about heaps. Friday we will talk about heaps. Your challenge 2, which was released last Wednesday, is due on Friday. So please take a look at that if you have not already. It's about stacks and queues. After this week, next week we will have an exam. So on Monday we'll do our review for the exam. I will post the kind of like the study guide summary sheet on Friday so you have it over the weekend. Monday we will do practice problems and you can ask questions. The exam will not be that different from the first one as far as the style goes. I'm trying to add more questions so as to make them worth less, because I know it's very annoying and upsetting when like you miss one little thing and then that's like 10 points or something. So I'm trying to do that without making it take too long for you. So trying to find that balance. Once we do exam 2, then we will start talking about graphs, and we'll keep going from there into the remainder of the topics we have for the semester. But the main thing to remember is that we will have exam 2 on Wednesday next week. Your programming challenge 2 is posted. It's due on Friday, and you can see it on Canvas. You can also sign up for a demo slot on Canvas as usual. The idea is to first of all, demo a working stack to the TA, and then they'll have you convert the stack to behave like a queue in the demo. And so that's just a little change. So there's stack and queue code on Canvas for you. You can download and look at it. It's got both the stack and the queue, and it's commented. It's some of what we looked at in class, and that should be something you can use for that demo. So be sure to take a look at that. Were there any questions about Programming Challenge 2 at this point? Shouldn't be too bad. But I'll check in again on Wednesday just to see if there's anything that comes up, but should be okay. All right. So if you remember, long ago we were talking about AVL trees, and in general we've been talking about trees a lot. Then we kind of moved from trees to binary search trees, and then to AVL trees. And so the reason we wanted to do this, right, is that there are some advantages of the binary search tree in general. So kind of our go-to example has been if we're trying to find an element in a collection of elements, and maybe they're ordered in this way, and let's say we've got an array, if we're just going to scan this array and look for, in our case, 90 here, we'll have to scan everything in the array before we get to 90 because it's at the end, which is almost the worst case. The worst case would be it's not in the array, so we have to scan everything. But if we had this same data arranged in kind of this better format, we don't have to do nearly as many comparisons to find 90. And the format here is a binary search tree. And to refresh you on that, it's just the idea of a tree where each node can have up to 2 children. And the left child is always less than the node, and the right child is always greater than the node. And that carries down this tree. And so you can think of each node as being its own little tree, if you like, a subtree. And so we see if we take that, and if we take kind of an example like this and we make it much, much larger, when we look at our runtimes, we get big theta of log n for our tree. And you can see the reason for that is that when we come through the tree searching for something, right, each time we make a decision, we're kind of cutting it in half, right? Whereas if we're just scanning, we're still got this linear set of things to go through. And so that's the main advantage of a binary search tree and why it's such an important data structure that's used in a lot of things. However, we kind of came to this unpleasant truth that a binary search tree alone can kind of go badly. So we build the binary search tree, as like the elements come to us, right? Let's just kind of imagine it that way. Like you've got either like a stream of elements coming in, or you've just got a bunch of elements in a file and you're just reading them, and you don't know what order they're in. And if they're kind of in a nice randomized order, things work out well. Your tree will probably be pretty good. However, if the elements are already in order, for example, when we build our tree, we end up with something like this, because each element's bigger than the one before it, right? So we just get this long line, which is essentially a linked list, and now we've lost all of our advantages, right? We can't, just cut out half of the search space each time because it only goes in one direction. And so we need a solution to this so that we don't end up with unfortunate trees like this that don't help us. And so the idea is that we can, as we build our tree, make sure that it maintains these properties that are beneficial to us so that it never becomes that long line that's just linear. And so last time we talked about AVL trees specifically, and we talked about doing these rotations to maintain the balance of a tree. And so today we're going to go through that again, and we'll go into it in a little more detail, kind of going through all of the cases that can occur, and looking at how this helps us keep a tree that is still very efficient. So here we go. This is the basic idea. We've got something that we would say is not good and something that is good. Same set of numbers that we're looking at. And if we were just building a binary search tree in the normal fashion, this all depends on the order in which the numbers came to us. Because we build the tree, we start at the beginning, and then we go left, right, depending. And so the idea is we want to stay on this good side of things, regardless of how the numbers come to us. And so essentially what we're saying is how can we prevent these binary search trees from becoming inefficient? And inefficient meaning they become unbalanced. They're heavily to one side or the other. They're not that nice, full-looking tree. And so we arrive at balanced binary search trees. And there are a lot of ways to balance a binary search tree. AVL trees are one way to do that. And they're a pretty good way. They're actually a pretty strict way of doing it. A lot of the ways that are actually used in practice are a little more forgiving. They let the tree be more unbalanced than this at times. But in general, there are a ton of algorithms for balancing binary search trees, and they all kind of do the same thing in that they make sure the tree maintains a property that allows it to still be efficient for us and well distributed. So we're going to talk about AVL trees. AVL is for the creators of AVL trees. So it's their last names, AVL, as you can see there. And this is one of the earliest approaches to balancing a tree, and it is a pretty good one. Like I said, there are a bunch of other ways. None of them do anything that's more efficient necessarily. There are minor trade-offs, and they usually have to do with constant factors. And so AVL trees are a pretty good way to balance a binary search tree. And so the idea is that we are balancing based on the height of each subtree. And so we'll be trying to keep heights meeting a certain criteria. So if we think about just balancing a tree in general, we can think of just a few basic examples, right? Okay, so if we have just one node, which is technically a tree, right? Technically a binary search tree, well, that's fine because there's nothing else you can do with that, right? If you've got something like this, just ignore the 90 here, well, this is all you can do here, too, right? You've got 3 elements, so 1 has to go on this level, and then 2 have to go on this level. Okay, add 90. Now you've got another level, but there's really no other way to arrange this to make it more compact, right? You might if you shuffled everything, you're still going to have 3 levels here. There's no way to change that. But if we've got something like this, right? So we've got 70, 89, and 90, and they've kind of done that thing where they're in a line. That could be better, right? And even if it's just a little bit better, right? So we could arrange it just like this, and now our tree is more balanced. I mean, we look at it, we can see that now we've only got 2 levels and the same representation. And so there's a question we have to answer first when we start to do things like this, and that is this okay?
Yeah.
Yeah, it is okay. Why is it okay, though? And there are 2 things that we have to keep in mind anytime we're going to rearrange things in the binary search tree. The first thing is it always has to stay a binary search tree, right? Wouldn't make much sense to just suddenly make it, some other kind of tree with like 4 or 5 nodes coming out of one node. That wouldn't work. So that's pretty obvious. The other thing that we have to do is we have to preserve what's called the in-order traversal. And if you remember, we talked about doing a pre-order traversal, a post-order, and an in-order. And so remember we did a trick to do this where we drew little lines on the nodes. And then if you draw around those, you can get your in-order traversal like that. So if you look at the in-order traversal for each of these, they're identical. So even though we've changed the structure here, the in-order traversal is the same, and that's what matters. And you'll notice in-order makes a lot of sense here for a binary search tree. In-order is literally the elements in order. And in terms of integers, from smaller to larger, but any kind of object you have, just the relative comparison. And so that's something just to kind of remember anytime we manipulate this, and this could be part of a much larger tree. We just have to be sure that whatever we do does not change this property so that the in-order traversal is different, because everything can kind of map back to the in-order traversal, and if it changes, it will break everything else. So when we're thinking about maintaining the balance of a tree, we can kind of approach it a step at a time. So don't think about an existing tree or anything. Let's think about it as we build a tree from nothing. So what we're going to do as we build the tree, right? And you can also think about removing things from a tree, but let's just talk about insertion for now. So we insert a node into the tree. And the way we decide where it goes, we just follow the binary search tree thing, left, right, until we find its little spot. Once we've put it in the tree, now we need to look and see if the tree is balanced. And so I'm kind of going to refer to that as a detection step. So after we do an insertion or a removal, we then need to kind of analyze just the portion of the tree that we've affected to see if it's still balanced. If it's not balanced, then we need to rebalance it, and I'm going to call that just kind of a repair step. And this all happens on the insertion or removal. So it's not something we do separately. Every time we change the tree, this is done as part of that. And importantly, and you'll somewhat see this, these steps are constant time. So they are pretty much free in terms of taking CPU cycles, and that helps us have a nice efficiency with this data structure. So we're doing this for every add or remove of a node, and we only need to worry about the node that we've inserted or removed, and any of its ancestors, so nodes above it. You don't need to worry about, so when you insert it, it will be a leaf, right? So it won't have any children. But everything above it, all the way up to the root, has to be looked at to see if things have changed, because that's what's affected. Now, anything else that's not in that path is fine, by definition. It hasn't changed at all. So this is also pretty efficient. And so the tree is always balanced at the beginning and end of our operations. Okay. So in order to actually do this, to detect if a tree is balanced or not, We're going to compute something that's called the balance factor. You'll also hear this called skew sometimes. How does this tree skew? And the idea for an AVL tree is pretty simple. And the idea is that the difference in height between any node's right and left subtree should not be more than 1. And so in order to talk about that, we've got to remember what a node's height is. And that may not be super intuitive always. So there are 2 ways that I like to think about height. These are 2 ways. They're both valid. So this first way of thinking about height of a node, and a node just being any node in the tree, you can think that the height of a node is equal to 1 plus the maximum of the height of the left subtree and the height of the right subtree, so whichever one is larger. And so if you want to do that, you need to have this convenient fact, and this is just something we define for convenience. If you're talking about a null node, so like say I'm here on 90, right? And I'm like, okay, left child, what is it? Well, it's null. There's no left child. So we're going to assign that the value of -1 as its height. And that just makes the math work out a lot better for us. So just remember that. Now, if you don't want to remember all of this, which this is great for putting it into code, right? That maps really well. If we're just looking at this thing, right? Here's a way to think about it. The height of a node is the number of edges to the furthest leaf node. And so that's pretty easy to look at. So if you have a leaf, right? If you are a leaf node, 0. You are the leaf. So your height's 0. If you're like 57 here, well, the furthest away leaf node, 55, so 1 edge. 62, 1, 2, right? If you're 70, you have to look at the whole possibility of all the routes that could happen here because you're looking for the largest path.
It's 3.
3, yeah.
So we count, 70 leaf node, like, what is it? So what's 3? What are we counting?
So we're counting the edges here. So for 70, we're counting this edge, and this edge. And I mean, you can see, like, because this tree is pretty small, where else could we go from 70? Well, we could have gone here, then here, but that's only 2. We could have gone here, here, that's 2, here is 2. That one's the longest, it's 3. And so when you're just looking at these smaller trees in a diagram, I think this is the easiest way to find the height because you don't have to worry about, taking the max of these things and propagating it all up the tree. Now, when you're coding, obviously, it makes a lot more sense to do that.
So the height is 3.
So
70.
Yes, for 70, the height is 3. And these are for each node. Now, kind of just as an aside, since 70 is the root node, we can say the height of the entire tree is also 3.
So what's like the height for 73?
The height for 73, okay, so
0?
0, yeah, nowhere to go.
So for 89, it's just 1?
1,
Okay.
exactly, yeah. So pretty basic, but important for our balance. So here you go. Just overlaying what the actual heights are here. And I've kind of added in these little nulls just to remind us that there's null pointers there that don't mean anything. Okay. So we want to look at the difference in height between the left and right child. So here are our heights that we have. And one thing that kind of always surprises me, or I'll forget, is that, for example, you see, 89 and 62, they're at the same level here, but their heights are different. And that's because 89 has a child. So that's kind of a thing that, I don't know, it jumps out at me every time. Because it's easy to kind of get where you think, oh, the levels maybe are the same. And in some cases they are, but they're not always. So just something to keep in mind. Okay, so here are our heights. Now let's try to calculate this balance factor or skew factor. And so to calculate that, all we're doing is the height of the node's left child minus the height of the node's right child. Now, this is a convention that we're going to use left minus right. You could use right minus left. You just kind of have to flip everything when you do it. You'll see it done both ways, like in textbooks or in examples. For us, we'll do it this way. Okay, so let's look at our very simple one here. Just this one node is 70. And so what we can see is, okay, it's got these two null pointers. Their heights are -1. We just defined that. That's what that is. And so, and we know the height of 70 itself is 0. But to find the balance factor, we need to do the height of the left minus the height of the right. So we get -1 minus -1, which is -1 plus 1, which is 0. So the balance factor, or the skew, of that node is 0. Now, when we do this with more than a single node, we want to start down at the bottom. Usually it's just kind of the more intuitive way to do this, and also because we'll be computing this on things we're inserting, and so there'll be leaves. So on this tree, let's start down at 90, right? And so same thing here, 90 doesn't have any children, so its height is 0. And so when we do that math for its balance factor, which is -1 minus -1, we get 0 there as well. Here, we're going to be doing, so for 89, we're doing the node, the left child of 89, which is -1, minus, and then the right child, which is 0. So -1 minus 0, we get -1 there. Okay, that's fine. It's not a difference that's larger than 1. And when I say the difference must be within 1, like plus or minus 1. Just the
So
absolute.
even if it's -1?
Yeah, it can be -1, it can be +1, and it can be 0. Those are all fine.
But we're going, if it's -1, we declare it as 1, because they still just subtracted about 1.
So it'll still have a sign to it. And you'll see, like, if I had these in the other direction, it would just have the opposite sign. But it's okay for it to be, like, it's still not, it's still balanced in that case. Like -1, +1, and 0, those are all balanced conditions. We don't have to do anything. So if we move up this tree a little bit more, though, we move up to 70, right? We're going to do the same thing. So we say the height of the left node, which is -1 because it's null, minus the height of the right node, which is 1 in this case. We get -1, -1, and that's -2. That's not okay. So since we've gotten a -2, and you'll either get a -2 or a +2, that indicates that this tree is not balanced. And we saw that, right? We saw earlier that we could simply kind of rotate this tree around and make it more balanced. So that would be our signal that we need to do some balancing. Now, if we look at this version, just like the tree here, so we've kind of got the same thing for 90, the same thing for 89. If we look at 62 in this case, you can see that it's got -1, -1. It's also okay there. And then if we look at 70 here, we can see that its left child is 0, its right child is 1, 0 minus 1, -1. It's all okay. There's nothing we can do for that tree. Its balance factor is fine. And so this is kind of our general approach to detecting if a tree or a subtree within the tree is balanced or not.
What's the difference between that one that's 70 at the top have 2, but the one over in the middle has 2 also?
Yes, okay, so these are just the heights of these nodes. And yeah, like they don't factor into like, so for the balance factor of a node doesn't care about its own height, it cares about its children's height. Yeah, those are just kind of there for completeness so that you know what they are. Okay, so how do we fix it? We do what's called a rotation. And I think, so I'm not a fan of memorizing things or kind of doing like rote stuff, but when we think about rotations, and you can logic through them if you want, this identity here, this set of transformations is all that there is to it. And so if you know this, you can do it anywhere. And this is the kind of, if on the exam we do a rotation, I will give you this. You will not have to memorize this, okay? But let's talk about what this means, right? Let's see. Okay, so if we have a tree, and let's just imagine it looks like this. And we have a root y, and it has a child that's x, and it has a right child, and we're going to call that C. And these triangles, what they represent are subtrees. So it may not be one node, it may be a whole big tree down there, right? Same thing for A, okay? It could be nothing, it could be null, like there could be no child, or there could be a child that has 100 children after it. Doesn't matter. What we can do is if we do what's called a right rotation on y, we can take this and arrange it like this, and that's fine. It preserves the in-order traversal that we care about, and it preserves the binary search tree principles. In a similar way, we can go the other direction. So if we have a structure that we can look at like this, we can do what's called a left rotate on x and transform it into this. And that's fine. And this turns out to be all that we need. So we're going to go through some practical examples of this. And you can work out a proof of this easily, that this is okay. And the easiest way to do that is to just do an in-order traversal of each of them and see that they're the same. But let's just do some examples so that we get a good idea of how this works. Okay, let's build a tree from scratch. We're going to, first of all, insert a node 50. So there's 50, and I'm just going to draw the null children on there. So for completeness. And so as soon as we insert it, right, what are we going to do? We're going to say, what's the height of it? Well, it's 0 because it is a leaf. And then we're going to compute the balance factor. In this case, -1 minus 1, 0. Okay, it's fine, right? Obviously, it's just one node. Like, it's not going to be unbalanced. Okay, so now let's insert 60. So we add 60, binary search tree principle says that goes to the right, and it's got some null children. And so we're going to go ahead and compute this as well. So the way we do this, we've inserted 60. We'll compute the balance factor for it, which is -1 minus 1, we get 0 there. Then we're going to go up the chain until we get to the root. So we'll say, what is your parent? We go to the parent node, and we do that same computation there. And that's how we're going to do this. So you'll always start at the new thing that you've inserted, and do the computation there. If that's okay, you move up. As soon as it's not okay, you fix it, and then you move up and check again. So pretty straightforward. So that's fine. We've got 50 and 60. We'll go ahead and insert 70. And so now we start at 70. We compute our things, right? And most importantly, we find that, okay, 70's fine, 60's fine, but 50 is now out of range, right? Not in balance. So that's where our problem is at 50. Let's fix it. So here's what we have, right? This is our whole tree. Our problem is at 50. And this is kind of our one tool that we've got. And we want to use that to balance this. So
Can we determine whether to left rotate or right rotate because our numbers positive or negative?
yeah. And so I'll show you kind of once we get towards the end. There are just conditions like in code that check this. But conceptually, we can kind of overlay these things, right? Well, imagine 50 is x, 60 is y. These are some null children on A and B. And then anything down here will be C, right? And so if we apply that transformation, we can, so it's a left rotate. Now we can arrange our things how they are there. And I'll take away these overlays. And you can see that we've now got a balanced binary search tree, and it's still following the same traversal order. And so we fixed that with the left rotate. Okay. And so since our problem was at the root, it doesn't have any ancestors, so we're done in terms of inserting that. And so now we've got our tree like this, 70's inserted, it's balanced, we're happy. All right, so let's keep going. We'll insert 40. And I'll just ask you to believe that this is balanced based on there's really nowhere else for 40 to go that would be better. There's no arrangement that would be better here. So I'll move on and insert 30. Okay. So now we're going to do the same thing, right? We'll start here with 30, which we just inserted. And we're going to compute its balance factor, which we get 0. We'll compute 40's balance factor. And with that, we will get 1. And then we'll move up. And finally, we get to 50. And when we compute its balance factor, which is its left child's height, which is 1, minus right child's height, which is -1, so that's positive 2. And so at that point, we detect there's a problem here, right? Starting at 50. And so we haven't reached the root yet, but because we found this problem here, we stop and fix it at this point. So what we're going to do is we've got this chunk of the tree here, and we don't care about this thing that's in the box right now. So we're going to kind of just look at 50 downwards, because that's what we need to fix. Okay, and so here's our problem. Here's our nice transformation that we're allowed to do. So if we look at this and we overlay it so that it matches one of these, we can put y over 50, x over 40, a, b, and c, just like this, so that it matches this. And then we will do a right rotate on y. And I went ahead and put this part of the tree we don't care about over here. It's just fine, I'm just copying it. But we can rearrange this part so that it looks more like this identity. And if we get rid of these overlays, so we now have it transformed into this. And if you look at that, you can see, yes, obviously it's binary search tree. And if we compute the factors, we'll find that it is balanced. So remember that we've only done up to kind of this 40 point, so we do need to go check the root node, its parent, because we started fixing it before we got to the root. And so we don't have to worry about anything down here because it's all fine. So we're just going to go up to 60 and we're going to compute its balance factor, and we'll find out that it's actually okay too. So there's nothing else to do as part of inserting 30. So everything is good with our tree at this point. Okay, so now we will insert 20. And when we insert 20, it kind of goes all the way to the left, right? We start computing our things. We start from 20, we go up, up. Everything's fine, 0, 1, 1. We get to the root, and now we have a problem. Because our balance factor, or our skew, is 2, which is out of range. So we need to fix that. And how do we do that? Do a right rotate. Yep. Again, we're just kind of mapping what we have up here in this identity down to our reality here. Get rid of those overlays for you. And you can see the right rotate rearranges things like this. You can see binary search is maintained. That is all fine. And again, since that was the root that had the problem, it has no ancestors. So the insertion of 20 is good. We don't need to do anything else. Okay, let's insert 45. Okay, so we insert 45, and you can see it flows down this way. Okay. So we start here, we compute the balance factor here, we go to the ancestor 45, balance factor. We keep doing that until we get to the root. And you can see all of these are fine, right? So we're good. We don't have anything to do here. All right. And now we'll insert 48. So when we insert 48, follow the comparisons, it kind of comes down here, and it ends up to the right of 45. Okay. So first thing we do, we look at 48 itself, compute its balance factor, 0, that's great. Look at its ancestor, balance factor there is -1, that's fine. We go to the ancestor of 45, and now the balance factor for 50 is 2, and that's a problem. So we're going to, even though we haven't made it all the way up to the root, we found a problem, we're going to stop and fix the problem before we go any further. And so we're going to, for the sake of the space of the slides here, I'm just going to ignore the rest of the structure for right now. We're just working on 50 and below. So that's what I've pulled out here. And you can see the balance factors for that. And so let's just try something here. We'll try to do a right rotation on it. So we stick our identities, our labels there to match that, and then we reconfigure it, and we rotate it, and we compute our balance factors, and it's -2 now. So it's still not balanced. So in this case, that right rotation was not helpful. If we were to try to do it the other way, that would also not be helpful.
Wait, why the right rotation? Why the 48 didn't stay stuck to the 45?
The what?
Why the 48 didn't stay stuck to the, oh, because it's more. Never mind.
Yeah. So you can see we've done the rotation, but we've kind of ended up with just the mirror of what that is, and it's not balanced. So this is a case where it turns out sometimes one rotation will not fix the problem. And just so you don't get scared, at most there are 2 rotations. There's never more than that. So if we kind of just stop and we think about it for a second, just looking at this small example, right? What would make this better? Just
Put 48 at the top.
I mean, if we put 48 at the top, yeah, right? Because then to its right, 50, left 45. That'd be pretty good. And so we can think of it that way. You can think of it as 48 is the median value out of these in the middle. And so, yeah, we'd love to have this. This would be great. But only if this works, if it maintains that in-order traversal property, right? And so can we go from that to this just using rotations? And we can. So we're going to do multiple rotations. We'll do 2 rotations here. And we're going to do the rotation on the children of 50 here. We're able to do that. That's within its subtree. That's okay. And so we're going to left rotate at 45. And kind of there's your mapping on that. Point is that when we do that, we get this, which is just fine, maintaining all of our principles. And this looks a lot better, because this is something we can now rotate into being that optimal thing that we want, right? So if we take and we apply a right rotation on this at 50, then we can get that desired tree structure that we wanted to come out of this. And so once we have that, we can go ahead and compute our balance factors, right? And we can see that now, and remember the root of this is what we care about ultimately. Our balance factor there is 0, and our other balance factors are obviously okay as well. And so now we've rearranged this to be a balanced subtree. And so we can bring that back, these 3 here, put them back in place in the larger tree, and then remember, we still need to go up a couple to check and make sure everything's okay. So we'll go ahead and do that, and we'll look at the balance factor for 60 is fine, and then the balance factor for 40 also fine. So everything is okay there. And then we're done with that insertion. So that's kind of the most complex case. And obviously you can have kind of like the mirrored version of that, where rather than doing like left, right, you do right, left on the rotations. But essentially we've got, and you'll hear that sometimes called a double rotation. That's fine. And also for some reason, sometimes people like to like write it backwards, like left, right instead of right, left whenever it's not the actual order. There's lots of notational stuff around this. It's not a big deal as long as you know what's going on here. We'll keep it just straightforward. Like if we're going to the right, we'll call it right. And if we're going left, we'll call it left. And so we've built this tree, and everything is nice and balanced. And we can be sure that there isn't anything we can do to make it a better tree that's more efficient to navigate. So, thinking about this kind of programmatically, if you were writing the code for this, what do you do? And you can sit there and you can work out examples and identify this stuff pretty quickly. But there are essentially 4 cases when we're doing this. And so I'll call them the single right rotation, the single left, the left right, and the right left. Sometimes you'll see these called double, and left and right order could be whatever. But based on the way we're computing those balance factors, that will inform what we need to do, essentially. So when you're in the code, it's very easy because you can look at the balance factor and immediately know exactly what operation you're going to do, what pointers you're going to switch to point here and there. It's constant time, it's quick, and it's done. So if we were coding this is what we would do. I don't think we will code this as part of class, and I don't believe your challenges will need an AVL tree. You'll use a binary search tree, but it doesn't need to balance, I believe. If we do need to do it, we'll go through this code together. It's not complicated. It's just a matter of doing this every time you make this change to the tree. The only slightly more involved thing is doing like removals from the tree. And the only kind of thing that's difficult there is when it's not in code, but if you're just thinking about it, trying to keep track of what the root is relative to everything else. And when you remove something, you reassign things. But that's not a big deal. It's totally doable. So thinking briefly about the computational complexity of AVL trees and why balanced trees in general are so powerful. And they're probably one of the most important data structures that we have because they have so many nice properties. So if you think about searching for an item in the tree, the runtime of that is big theta of log n when it's a balanced tree because you are kind of dividing that in half every time as you go. Also, interestingly, these trees can be used for things like sets and sequences. So you can find like the kth item, where k is a number, in the tree in log n time. And it's just a matter of kind of remapping some things. But that is totally possible, and that is why they are used for a lot of data structures. Similarly, if we're inserting something into the tree, just inserting one thing and balancing it, log n time, right? Because all we have to do is find the place to put it and then hook up the pointers. If we need to balance, we reshuffle those pointers. That's all constant time. So log n, where n is the number of nodes in the tree, I should say. You'll sometimes see also h mentioned, where h essentially equals log n. H is the height, roughly, of the tree. But log n is what we'll typically call it. Same thing for removal and balance, log n there. And then finally, if we are building this tree from a set of n unsorted elements, thinking about how long does that take? So for each element that you insert, right, is log n time. And you're going to do that n times, so you end up with n log n. And so if you've not run across any examples of where that is the complexity, this is one of them. That's where something like n log n comes into play. So here are some applications of binary search trees. They are used in lots of things. Important to note, mostly we use them for things that are where we can have the full data set in very, very fast memory, so in RAM or something like that. If we have something where we have to have it spread across multiple petabytes of disk, then we typically use something called like a B tree, which is kind of a amped up version of a binary search tree, which has many, many more than 2 children and lets us navigate that more efficiently. We're going to have a quiz on Wednesday, and on the quiz, the things we're going to do are compute the heights of nodes and compute the balance factors of nodes. And then you might be asked if it's balanced or not. So is it, -2 or 2? So that's all you'll need to know. We will not rotate anything, none of that. Just be able to compute these heights and compute the balance factor of the tree. And so that is all we have today. And I will see you on Wednesday, and we'll start talking about heaps.
So we just been like